Hello everyone, my name is Mukkula and I welcome you to my presentation on an application of modifier adaptation with quadratic approximation on a pilot scale plant in industrial environment. This work was done as a part of the research project Consens funded by the European Union. In this picture, we see a modular production plant developed in the F3 factory project. Our goal is to optimally operate a lithiation reaction in an intensified continuous tubular reactor in this modular plant in industrial environment, taking into account the process and safety constraints. The important modules of the modular production plant used in the lithiation process are shown in this figure. The reactant feed tanks are shown here. 3 reactants along with a solvent react in the tubular reactor shown here. The reaction mixture from the reactor outlet is then passed to the product tank. A PAT sensor, an NMR, is used to measure the concentration of some reactants and the product in the product stream. The NMR is placed in an explosion-proof ATEX certified module. I will come back to this slide in the second half of the presentation. In order to identify the optimal operating inputs of the lithiation reaction process, a mathematical model of the process is required. One can identify the optimal operating input for the process by solving an optimization problem, where a cost function is minimized, or by solving an optimization problem where a profit function is maximized. However, the challenge here is that the reaction kinetics is not known. Therefore, we do not have an accurate mathematical representation of the process. We propose to overcome this using real-time optimization methods. In the next 15 minutes, I will briefly present real-time optimization, and I will present in detail the real-time optimization method modifier adaptation with quadratic approximation. I will then present to you the lithiation reaction case study and a framework developed to establish a seamless communication between the optimization scheme and the plant without the need for manual intervention. Then I will present to you the simulation and experimental results, and finally I will end my talk with a short summary and outlook. Consider a continuous plant where U represents the input variables to the plant and Y represents the steady state measured variables from the plant. If a mathematical model that can represent the plant behavior accurately is available, one can identify the optimal operating input for the plant by solving an optimization problem where a cost function is minimized. However, it is very less likely that an accurate plant model is available. If the optimization problem is solved using a nominal model with plant model mismatch, the identified model optimum may not match with the true plant optimum. Several real-time optimization methods were proposed in the literature to handle plant model mismatch. Modifier adaptation with quadratic approximation is a modifier adaptation based iterative optimization method developed at our chair. It can handle both structural and parametric plant model mismatch. In general, iterative real-time optimization methods are applied in the following manner. Initially, the plant is given an input and the measured variables from the plant are used by the real-time optimization to compute a new input to the plant. This step is iterated until the input from the real-time optimization methods converge to the plant optimum. As seen earlier, the optimization problem using a nominal model where a cost function is minimized subject to process constraints does not identify the true plant optimum. In modifier adaptation, the objective and constraint function of the model-based optimization problem is updated iteratively to compute a new input. The objective function is modified by adding a gradient correction term, and the constraint functions are modified by adding both bias and gradient correction terms. The modifier adaptation scheme is applied in the following manner. Initially, an input is given to the plant. The measurement information from the plant is used to modify the objective and constraint functions, and the modifier adaptation problem using the modified objective and constraint functions is solved to compute a new input to the plant. This step is iterated until the input from modifier adaptation converges to the plant optimum. Modifier adaptation converges to the plant optimum if we have good estimate of the plant gradients. In modifier adaptation, the gradients could be approximated using finite differences. Also, additional plant evaluations are required to approximate the gradient. Moreover, it is crucial that the plant gradients are approximated precisely in order to converge to the process optimum. In modifier adaptation with quadratic approximation, as the name suggests, a quadratic approximation is used for the approximation of plant gradients used in modifying the model-based optimization problem. A general quadratic function is shown here. It is a function of parameters p and input variables u. The quadratic approximation function can be fitted when there are at least as many data points as the number of parameters to be identified. In modifier adaptation with quadratic approximation, finite differences is used for gradient approximation if there are fewer points than the number of parameters to be identified. The number of parameters in a quadratic function can be computed using this empirical equation, where nu is the number of manipulated variables. If there are more data points, screening algorithms can be used to choose points that are to be used for quadratic approximation. In general, the screening algorithm chooses anchor points represented by these points such that they are distributed around the point at which the gradient has to be approximated. The data points inside the inner circle are used to increase the accuracy of the gradients. In addition to the screening algorithm, a criticality check criterion is used to ensure that the anchor points are not distant lying from the point at which the gradient has to be approximated. It works in the following manner. It checks if any of the anchor points used for quadratic approximation are lying too far from this black dot, that is the point at which the planned gradient has to be approximated. The radius of the outer circle, although as a tuning parameter, it was said to be twice to that of the radius of the inner circle, which is already a tuning parameter. This criticality check is performed only if the new input is close to the already known best input. Usually, such a scenario happens when the iterative optimization scheme is close to converging to the true planned optimum. Let us look at a case when not all the anchor points are within this ring. In this example here, one anchor point is lying outside the ring, and at the same time, the optimum identified is not very far from the best known input. In such a case, the criticality check algorithm suggests to not probe the identified optimum represented by the green point in this figure. Instead, it updates the input for the next iteration to be this blue point. By doing so, evenly distributed anchor points are available for the next iteration. In modifier adaptation with quadratic approximation, if quadratic approximation is used for gradient approximation, an additional trust region constraint is added to the modifier adaptation problem. Gamma in the trust region constraint is a tuning parameter. The modifier adaptation with quadratic approximation scheme is applied in the following manner when there are sufficient data points for quadratic approximation. In each iteration, upon building a quadratic approximation model, the quality of the nominal model is compared with that of the fitted quadratic approximation model. If the quality of the nominal model is better than that of the fitted quadratic approximation model, the modifier adaptation problem is solved to compute the next input for the plant. Instead, if the quality of the quadratic approximation model is better than that of the nominal model, an optimization problem based on quadratic approximation model with the trust region constraint is solved to compute the next input for the plant. Before applying the input to the plant, the criticality check step is performed, and if required, the criticality check step updates the input. These steps are performed iteratively to converge to the plant optimum. This is modifier adaptation with quadratic approximation briefly. For more information about the algorithm, please have a look at this article. Let me now present to you the lithiation case study. 3 reactants, aniline represented by A, lithium bis trimethylsilyl amide represented by B, and fluoronitrobenzene represented by E react in a 5-step reaction mechanism in a tubular reactor at room temperature to produce lithium 2-nitrodiphenylamine represented by H. However, the information about the reaction kinetics is not known. We know that the reaction is fast and exothermic. Instead of the 5-step reaction mechanism, the nominal model considers a single-step reaction leading to plant model mismatch. For safety reason, the temperature in the reactor has to remain less than 54 degrees Celsius, and the goal is to maximize the profit function shown here. We want to maximize the concentration of the product in the product stream. In the profit function, WA, WB, WE and WH are the weights which reflect the cost of the reactants and the product. The bounds on the feed flow rate are 3 and 8 kg per hour. The concentration of the product H is measured using the online NMR sensor. In order to run the real-time optimization scheme at the real plant autonomously, it was necessary to establish a reliable communication between the real-time optimization and the Siemens PCS7 control system of the plant. and between real-time optimization and the SQL database of the online NMR. A schematic of the communication scheme used for the experimental implementation of the real-time optimization is shown in figure. The PCS7 control system has an OPCDA server installed. The temperature of the reaction mixture at the reactor outlet is recorded in the OPCDA server, from which this information is read by the real-time optimization. The SQL database of the online NMR records the concentration of the reactants, byproducts, and the product. This information is read by the real-time optimization from the SQL database. The input calculated by the real-time optimization scheme is written onto the SQL database of the online NMR, which writes it onto the OPCDA server of the PCS7 control system. This Siemens PCS7 control system finally applies the input to the plant. This figure illustrates the input moves and the evolution of the profit function when modifier adaptation with quadratic approximation scheme is used. The red colored markers represent the feed flow rate of component A. The blue colored markers represent the feed flow rate of component B, and the green colored markers represent the feed flow rate of component E. The blue dashed line represents the profit function, whose y-axis is on the right hand side of the plot. The true plant optimum is shown here. In order to take into account the process noise, the input flow rates and the concentration measurement in the plant profit function are corrupted by Gaussian noise. It can be seen that in the initial few iterations, when there are not many data points, finite differences is used for gradient approximation. Before the first iteration, after performing plant perturbations according to finite differences, 9 additional plant perturbations are performed to benefit early from the quadratic approximation. These additional perturbation inputs are chosen such that they are well distributed over the operating region. Once the plant measurements for all applied inputs are available, the modifiers are computed and the modifier adaptation problem is solved to compute the next iteration input, that is U1. From the first iteration onwards, quadratic approximation was used for the approximation of the plant gradient due to the availability of the minimum required number of data points. The real-time optimization scheme already identifies a near optimum operating input U3 in the second iteration. Although the optimum of the plant and the nominal model are close, the optimization problem using the quadratic approximation model is chosen by the iterative optimization scheme over the modifier adaptation scheme using the nominal model, as the approximated quadratic approximation model represents the plant measurements better than the nominal model. After identifying a near optimum input U3, the iterative optimization scheme performed several exploratory moves to satisfy the criticality conditions before it converged to the known plant optimum. This figure illustrates the input moves and the evolution of the profit function when modifier adaptation with quadratic approximation scheme is used for optimizing the real plant. For the experiment, the screening algorithm for choosing anchor points was suppressed. This is done to use all the available data points for fitting a quadratic function to avoid oscillating input set points from the real-time optimization scheme, which can be caused by flipping of the quadratic function. In the beginning, plant perturbations were realized to approximate the plant gradients using finite differences. Additionally, 9 additional plant evaluations were performed to ensure the availability of well-distributed data points for quadratic approximation. From the first iteration onwards, quadratic approximation was used for the approximation of the plant gradient due to the availability of the minimum required number of data points. The third iteration input is already close to the theoretical plant optimum. During the 7th iteration, an unplanned event took place. The feed container was changed and the weight percentage of component B in the feed was increased. This information was not made available to the control system. Nonetheless, as the control process was not yet stationary, it was reflected in the plant gradients that were computed from the quadratic approximation, and the control scheme responded by making moves to improve the plant performance. The improvement in the plant profit over the iterations is shown here. The input moves between the 3rd to the 7th and from the 9th to the 18th iteration are caused due to the tuning of the algorithm, specifically by not employing the screening algorithm and the criticality check. This has the positive effect that the algorithm reacts quickly to changes in the plant, but leads to slight oscillating inputs, which however have almost no influence on the profit. Nonetheless, the online optimizing algorithm showed a very good performance, driving the plant to the optimal operation in the presence of significant structural and parametric plant model mismatch. To summarize, we reported the development of an online real-time optimization solution for a highly innovative containerized continuous production process in a pilot plant. Modifier adaptation with quadratic approximation is a novel iterative optimization scheme that uses a plant model as well as measurement data. It was chosen as a suitable algorithm for the case study. The simulation results show that the real-time optimization scheme is capable to drive the plant to its optimum despite significant plant model mismatch in few iterations. We have validated experimentally that the combination of online NMR measurements of the concentrations at the plant outlet with the real-time optimization can drive the plant to an optimal operation despite significant deviations between the model used in the optimization algorithm and the behavior of the real plant. In our future work, we will focus on developing a standardized approach for choosing the tuning parameters in the modifier adaptation with quadratic approximation scheme. Thank you very much. For questions, please contact me at anveshreddy.gottumukkula@tu.min.de.